January 16th, Ukraine didn't hunt Oreshnik in the sky. They targeted the stockpile on the ground. While Russia concentrated launchers, fuel systems, and command vehicles inside a fortified Belarusian site, Ukraine waited for one condition: everything packed into one place. Then they struck the warehouse logic, not the missile speed. What followed wasn't an interception. It was a controlled collapse, turning a strategic missile reserve into a chain reaction that erased months of production in minutes. At 11:42 p.m., eastern Belarus appeared calm. No airspace restrictions were issued, no emergency alerts were active, and civilian flight routes remained unchanged. From the outside, the region showed no visible signs of military activity. Inside a restricted military installation not listed on public maps, activity had already intensified during the previous 10 days. Commercial satellite data recorded a 412% increase in residual ground heat within the compound. While surface temperatures fell to -8 degrees Celsius, several underground zones remained consistently warm, indicating sustained operation of heavy electrical and support systems. Logistics movement followed a defined pattern. Between 11 p.m. and 4 a.m., heavy transport traffic increased by over 340%. Vehicles weighing 50 to 55 tons entered the base at fixed 47-minute intervals. Rail spurs, inactive since the early 1990s, were reactivated, delivering sealed containers through reinforced access points unused for more than 30 years. Signals intelligence confirmed a parallel escalation. Encrypted military communications around the site increased ninefold, with multiple uplinks remaining active for up to 72 continuous hours. No exercises were announced, and no official deployments were declared. All observable indicators pointed to the same conclusion. The site was not preparing for movement. It was preparing for completion. By 12:18 a.m., intelligence analysis confirmed the nature of the deployment. The site was hosting the first fully assembled Oreshnik strategic missile battery ever positioned outside Russian territory. This was not a rotation and not a drill. It was a permanent forward deployment. Each Oreshnik launcher carried a solid fuel missile designed to operate under internal temperatures exceeding 4,600 degrees Celsius during boost phase. Estimated terminal velocity ranged between Mach 9 and Mach 10, placing interception probability below 15% under standard NATO modeling. The cost of the system reflected its role. One complete launcher package, including command vehicles, power units, and support equipment, was valued at approximately $400 million. Maintaining operational readiness required more than 90 specialized personnel, continuous encrypted data links, and electrical demand comparable to a mid-size industrial facility. By relocating the system into Belarus, Russia shortened flight time to several European capitals to under 8 minutes. Satellite intelligence reveals full missile system assembly. This was not a tactical improvement. It was a strategic signal. The battery was not meant to be used. It was meant to exist. Because the moment Oreshnik failed, whether intercepted, sabotaged, or destroyed, the credibility of the entire system would collapse with it. At 1:07 a.m., Ukrainian command elements confirmed the target was within effective strike range. Continuous drone surveillance and satellite updates every 90 minutes provided launcher coordinates with sub-meter accuracy. Several long-range attack options were technically viable. None were approved. At that time, only 6 Oreshnik launchers had arrived at the site. Fueling operations were incomplete, and multiple missiles remained in transport configuration. A successful strike would have destroyed visible equipment, but preserved most of the system's production value. Operational analysis showed that an early attack would eliminate no more than 20 to 25% of the battery's strategic worth. Remaining components could be redeployed or rebuilt within weeks. That outcome was assessed as insufficient. Instead, planners identified a higher value objective. A fully assembled Oreshnik battery required 14 to 16 months of synchronized manufacturing, rare materials, and components already restricted by international sanctions. Destroying all launchers simultaneously would erase an entire production cycle rather than damage a single unit. The risk of waiting was substantial. Once fueled, Each missile carried volatile solid propellant capable of generating internal temperatures exceeding 4,000 degrees Celsius. Any strike under those conditions risked uncontrolled detonation. Despite that risk, the directive was issued. No launch authorization, no preemptive strike, continuous tracking only. The confrontation was no longer about firepower. It was about timing. From that moment forward, Ukrainian command was not preparing to attack the base. It was waiting for the base to finish assembling itself. By 2:41 a.m., the pattern changed. Within a 6-hour window, all remaining Archnik components were moved into the same operational zone. 10 launchers, command vehicles, fuel units, and support equipment were concentrated inside a radius of less than 600 meters. Movement logs showed no further outbound traffic. Everything was arriving, nothing was leaving. Thermal data escalated sharply. Ground temperature inside the compound rose by over 480%, driven by continuous fueling and power system activation. Independent analysts estimated that the site now contained solid propellant with an explosive yield equivalent to more than 1,100 tons of TNT. At this stage, the facility crossed a critical threshold. Once solid fuel loading reached final pressure, the missiles could no longer be safely relocated. Any attempt to disperse the launchers would require depressurization cycles lasting several hours, a delay incompatible with combat conditions. The base had effectively locked itself in place. Satellite imagery confirmed that all blast doors were sealed. Internal ventilation systems were running at maximum capacity, and emergency response vehicles were repositioned closer to the bunkers. These were not defensive measures. They were indicators of final Ukraine, delays the strike, and waits for the perfect moment assembly. For Ukrainian planners, the significance was immediate. The target was no longer a group of vehicles. It was a single system. If one structure failed, secondary ignition would follow. If ignition occurred, containment would be impossible. From this point forward, the situation could no longer be reversed. Everything that had been separate was now connected. And once connected, it only required one trigger. At 3:12 a.m., the operational plan was finalized. Ukraine did not assemble a large strike formation, no mass launch, no saturation wave of aircraft. The entire mission relied on a package smaller than most routine patrols. The strike group consisted of 2 F-16 Block 70/72 aircraft and 10 long-range unmanned aerial vehicles. That was the full force. No reserves were allocated. The cost difference was extreme. The total value of all assets committed to the operation was estimated at under $8 million. The target they were preparing to engage exceeded $4 billion in combined strategic and manufacturing value. The aircraft would not cross the border. All weapons were programmed for standoff release well outside hostile airspace. Flight paths were calculated to remain below detection thresholds and avoid early radar correlation. The unmanned systems were equally limited in scale. Each drone carried a small gasoline engine, basic guidance hardware, and a warhead weighing less than 80 pounds. Individually, they posed little threat. Collectively, they were designed to shape the battlefield rather than destroy it. The objective was not immediate damage. It was control. Every element of the package was assigned a precise role, timed to the second. No platform was expendable and no action was redundant. The entire sequence depended on synchronization rather than firepower. From this moment forward, the operation could no longer be adjusted. The next phase would not be decided by planning. It would be decided by execution. At 3:47 a.m., the first phase was initiated. From well inside Ukrainian airspace, the lead F-16 released 2 ADM-160 MAL-DJ decoys. Within seconds, both units activated pre-programmed electronic profiles designed to replicate high-altitude strike aircraft. Russian early warning radar reacted immediately. Within 90 seconds, the S-400 surveillance system classified more than 25 separate aerial contacts. Radar returns suggested multiple large targets approaching at altitudes above 25,000 feet, with signatures consistent with manned aircraft rather than unmanned systems. The response followed doctrine. Target prioritization algorithms shifted all available tracking capacity toward the perceived high-threat sector. Fire control radars locked on. Launch authorization was granted automatically once correlation thresholds were met. Between 349 and 353 a.m., 8 S-400 interceptor missiles were fired in rapid sequence. Each interceptor carried an estimated cost exceeding $2.5 million. None engaged a real aircraft. The deception achieved its primary effect. By expanding the interceptors, the battery entered a mandatory reload cycle requiring 35 to 40 minutes. During that window, long-range air defense coverage was effectively unavailable. More critically, radar operators interpreted the engagement as a successful decoys and drones overwhelm Russian air defenses intercept. System logs recorded confirmed kills against the false targets. Attention shifted away from low-altitude sectors. While operators focused upward, the actual threat profile remained below 150 feet, masked by terrain and clutter. At that moment, the most expensive air defense network in the region was operational in form and blind in effect, and with the upper layer occupied, the next phase moved forward unnoticed. At 4:02 a.m., the engagement shifted to the inner perimeter. 6 unmanned aircraft entered the final approach corridor at altitudes between 120 and 160 feet, moving below the effective tracking envelope of long-range radar. At that height, detection relied almost entirely on short-range fire control systems. Panzer S-1 and Torm M2 units reacted immediately. Within seconds, multiple tracking channels were activated. Each system attempted to engage several targets simultaneously, approaching its maximum processing capacity of 4 to 6 concurrent tracks. Beyond that limit, sensor refresh rates began to degrade. The effect was measurable. Reaction time increased by over 40%. Target handoff between radar and optical systems became inconsistent. Engagement windows narrowed to just 2 to 3 seconds per drone. Fire volume surged. Panzer cannons discharged at rates exceeding 4,000 rounds per minute, expending tens of thousands of 30mm rounds in under 2 minutes. Missile reload crews were ordered forward while active engagements were still underway, a violation of standard safety procedure. They forced the defense network to commit every sensor, every launcher, and every operator to the wrong layer of the fight. Thermal imaging showed all short-range systems operating continuously with processor loads peaking above 95%. At that level, no redundancy remained, and when a system reaches its physical limit, it cannot adapt. It can only continue doing the same thing until something arrives that it was never free to see. At 4:11 a.m., the decisive phase began. While the inner defenses were fully engaged at low altitude, the second F-16 remained outside hostile airspace, flying a stable release profile more than 95 kilometers from the target. No radar warning was triggered. No tracking alert was generated. 4 AGM-158 JSMER missiles separated from the aircraft in sequence. Each missile descended immediately after release, stabilizing at altitudes between 40 and 60 feet, following preloaded digital terrain maps. At that height, radar detection probability dropped below 10%, even for active fire control systems. The missiles did not rely on external guidance. Internal inertial navigation corrected position every 0.0202 seconds, while imaging infrared seekers compared live thermal data against stored facility signatures. Even full-spectrum jamming would not have altered the guidance solution. Instead of targeting reinforced blast doors, the missiles were programmed to strike structural weak points. Analysis identified ventilation shafts and pressure control corridors where concrete thickness dropped from over 6 meters to less than 2.5 meters. Impact velocity exceeded 900 kilometers per hour. Penetration occurred before detonation. Delay fuses triggered inside enclosed spaces, maximizing internal overpressure rather than surface damage. What followed would no longer be controlled by weapons or pilots, but by physics inside a sealed facility packed with energized solid precision strike triggers, total missile site collapse fuel. And once that reaction began, nothing on the surface could stop it. At 4:16 a.m., the internal containment threshold was exceeded. Inside the reinforced bunkers, solid fuel propellant ignited under confined conditions. Unlike liquid fuel, the material required no external oxygen. Once initiated, combustion accelerated instantly, generating temperatures estimated above 5,000 degrees Celsius. Internal pressure rose beyond design tolerance in less than 0.8 seconds. Structural sensors recorded failure across multiple load-bearing points simultaneously. Steel blast doors weighing several tons were forced outward, traveling hundreds of meters before impact. The primary bunker roof collapsed inward, followed by a secondary ignition sequence across adjacent storage sections. The resulting thermal plume rose nearly 900 meters, visible on infrared satellites operated by multiple civilian providers. Seismic monitoring stations detected ground vibration equivalent to a 2.4 magnitude event, confirming a chain reaction rather than a single detonation. 2 mobile launchers attempted evacuation procedures. They did not clear the perimeter. Follow-on unmanned strikes impacted exposed missile canisters, triggering additional secondary explosions. Vehicle remains were scattered across a radius exceeding 300 meters, rendering recovery impossible. By sunrise, the site had ceased to function as a military installation. Post-strike analysis confirmed the complete loss of 10 Archnik launchers, all associated command vehicles, fueling systems, and calibration units. The destruction represented more than 14 months of synchronized manufacturing involving components that could not be replaced under existing international restrictions. Financial estimates place total losses between $4.2 and $5 billion. The strategic cost was higher. A Resnik had been intended as a deterrent platform. Its value depended on credibility, secrecy, and concentration. All 3 were eliminated within minutes. What remained was not a damaged system, but a deleted capability. The battery was not neutralized in flight. It was eliminated before it could be used. By the end of the morning, one of Russia's most heavily promoted weapons programs no longer existed in operational form, and the balance it was meant to enforce had vanished with it. This operation did not succeed because of speed, firepower, or advanced missiles. It succeeded because of timing, intelligence, and patience. In modern warfare, the most dangerous moment is not when a weapon is launched, but when it is allowed to fully assemble. A system worth billions was erased not in the air, but on the ground before it ever fired a single shot. Now, I want to hear from you. Which part of this operation mattered most? The deception, the timing, or the precision strike? Leave your thoughts in the comments. And if you want more clear breakdowns like this, make sure to subscribe.